All right. Welcome, everyone. Thank you for coming. It's a pleasure to have here Dr. Gaskill from the Navy Research Lab today with us. He'll be talking to us about controlling epitaxial graphene growth. And Dr. Gaskill got his PhD from University of Oregon, or Oregon State University, sorry. And he's extremely well published. He was a National Research Council postdoc fellow at NRL, and then subsequently became a member of technical staff in 1987, where he is, at NRL that is, where he's conducted research in the epitaxial growth, in situ characterization of growth, and electrical and spectroscopic characterization of various semiconductors. And he's currently the NRL PI for the DARPA SERI program. It's a pleasure to have you. Thank you.
Thank you very much, Hamid, and all the members of the faculty and staff here at NC State. It's been a long time since I've come down here. My first problem is to try to get my slides up here. Yay, all right. So if you'll bear with me for a few minutes as I get used to your projection system. The work that I'm about to describe is actually due to the contributions of many, many people at Naval Research Lab, and I will also acknowledge them later on in the presentation. Thank you. All right, so all of you have heard about graphene, unless you just came out of a cave in the last few days. The Nobel Prize was awarded in graphene just a couple years ago to Andre and Kostya. So it's a wonderful material, and lots of dreams have been built upon it, and some of which may even become reality. And that's some of the things I'd like to touch upon today. So graphene. Graphene probably started in the laboratories that originated in New Jersey with Thomas Alva Edison. Thomas Edison had a laboratory assistant named Edward Acheson, and he loved doing experiments. And he did all sorts of great work for Edison, and Edison rewarded him by making him his assistant lab manager. And so he got a job at a competitor the next year. And one of the things he did is he believed in the scientific method that Count Rumford was espousing, that is, using large currents to heat up materials to create new compounds. And so he used that approach, and he thought he made a material that would have been very hard, extremely good abrasive, which would be great for machining, which was very important in the 1890s. And so he created silicon carbide. And he didn't know it was silicon carbide at first. He called it carborundum. It's the same material that we know today. It's the material that edges all the tool bits used in every machine shop in the entire world. And so that was an amazing invention, but he didn't stop right there. He once again applied the electrical leads, heated up carborundum, and what happened was that silicon sublimed. And the first steps in the sublimation was leaving carbon behind. And that was probably the first time that man created graphene, because that was the first step. Of course, as it continues, it just makes graphite. And of course, Acheson, being a smart man, he knew that graphite could then be used as a lubricant. And so he took his knowledge of silicon carbide and graphite, and he applied it to the tool and die industry. And today, that company still exists. It's called Union Carbide. So Union Carbide started with graphene. And there's been amazing progress in just the last 8 years in the graphene business. And these 4 vignettes just give you a sample of some of the things that I find fascinating. You've heard about the roll-to-roll production of these 30-inch graphene films being developed in Korea that potentially for use in touchscreen applications. This is some work that a friend of mine up at Cornell, Mike Spencer, was doing. I find this one particularly fascinating. They have some nice SEMs up there, And so this is the closest we ever can come to imaging a one atom thick membrane. That particular bridge collapsed. So he was making suspended graphene bridges. A researcher at NRL, Jeremy Robinson, makes these graphene drums. And the drums have a very high Q, and it's a very narrow Q, so that means they're extremely sensitive to changes, to any mass that's put on the drum head. And so this drum could measure masses on the order of 4 or 5 atoms of gold, a change in mass on that magnitude. And at NRL, we're very much interested in using graphene for RF applications, making high-frequency field effect transistors. And here's an example of one of the first wafers that we patterned. And the application space for this is, as you get into the high frequencies, that allows you to do other type of sensors applications, such as looking through clothing. And if you've gone through the airport recently, you sort of know what I'm talking about. So all of this is because of sp2 bonded carbon. And a brief primer on what sp2 bonding gives us. The hexagonal structure consists of 2 interpenetrating lattices, so it's a 2-atom basis. And when you calculate the band structure, which was done in the 40s, you get linear bands in the vicinity of the K point in the Brillouin zone. And a linear band structure means that the effective mass of the carriers is 0. And that's the fascinating part. And so you could write the energy as a function of the wave vector k, and the proportionality constant is simply the Fermi velocity. And the Fermi velocity for graphene is the highest known for any material known to man. And so that becomes very interesting. In addition, you can have electrons as carriers or holes as carriers, and it's ambipolar. So there's no band gap between them, so you can switch an electron to a hole with very little energy loss. And this was verified experimentally many times. This is an example of the verification using angularly resolved photoelectron spectroscopy, also called ARPAS. And you can see the linear bands in the valence band in this particular figure. Lots of other amazing tantalizing properties. You can use an electrostatic gate to control the properties, the transport properties of the graphene. Yes, sir?
Effective mass very negligible, does it mean very low resistance, or what does that mean?
Well, it means that the carriers act as if they have no mass, so they can accelerate to their saturation velocity under a very weak electric field extremely quickly. And that becomes valuable for device technology. I don't know the figures off of hand, but for gallium arsenide, what is the saturation field is what, 10 or 20 kilovolts per centimeter? Whereas for graphene, it could be like 1 kilovolt per centimeter. It has high mobilities. Actually, the mobilities have been measured to be as in the hundreds of thousands for freestanding graphene, and that decouples the graphene from the surface that it resides upon, and the surface is limiting the transport of those charge carriers because of various scattering mechanisms. It supports very high current densities. It's all surface. There's no volume. It's just a single sheet of atoms. And it's also amenable to all the standard processing steps for silicon processing. And that makes it very attractive. About the only thing it's missing is it doesn't have a native oxide, because if you try to oxidize graphene, it evaporates. So you have to put your own dielectric down, and that has its own challenges, which I won't be touching upon today. There's other potential application space. One area I just happen to mention is because you have a very symmetrical IV response for graphene. That means it becomes very attractive for making frequency doublers or mixers, and that becomes valuable if you need to up convert or down convert signals from high frequency to low frequency. The thing that got us very excited about graphene is for low applied drain source voltages, you have in principle the ability extremely high cutoff frequencies. We're talking several terahertz. This is data calculated by James Champlain, and it's based upon realistic values taken from FETs that have been manufactured at NRL and HRL, just assuming gate lengths on the order of 30 nanometers. And you can see it's extremely fast material. And this bottom curve here, this is the state-of-the-art for the fastest 3-5 semiconductors, which are all based upon indium phosphide technology. And you can see that for very low drain source voltages, it exceeds the state-of-the-art by easily an order of magnitude. So that becomes extremely attractive, and that's one of the reasons why we're motivated to look at graphene for RF applications. So in today's topics, I've touched a little bit about what graphene and its potential applications are. Let me tell you next a little bit about how we make the graphene on the silicon carbide wafers. Silicon carbide, for those of you unfamiliar, is extremely hard material. It comes in a range of crystalline forms we call polytypes. There are two major hexagonal forms, hexagonal polytypes, which are known as 6H and 4H, based upon the symmetry of the atoms in the lattice. So as you can see in this particular image, you could grow boules of silicon carbide. This is a 6H boule. It's a 3-inch, 75 millimeter, and it's made by 26 Corporation. And you can slice this into wafers, and you can buy them today. You can go and you can get out your credit card and buy a wafer, and it'll be on your doorstep in a week.
You can actually write on the thing duration.
I know. I'm not used to this. What I want is a wooden stick I can point to it or something like that. Now, because of silicon, we're going to start writing on this now. Because silicon carbide has, what's a great color? How about red? Silicon carbide is a polar material. So one face is a silicon face and the other face is a carbon face. So here's the silicon face and here's the carbon face. And so if you have a wafer, one side will be the silicon face, and if you flip it over, the other side will be the carbon face. And that becomes very interesting because the properties of graphene grown on those two faces are completely different. And you're going to find out more about that in just a moment. Now, as I mentioned, the silicon carbide, it's a sublimation process. So I remove silicon atoms, and that allows the remaining carbon atoms, which have very low vapor pressure, so they don't disappear easily. They can reconstruct into the graphene layer. But I need to remove 3 bilayers of silicon carbide. So I have to remove, here's a bilayer here, here's a bilayer and a bilayer. So I have to get rid of all 3 of these bilayers to get enough carbon atoms to make a single layer of graphene. And so that means the process of making graphene, it is below the surface that you started with. And so you might call it inverse epitaxy. Okay, the way we do it, it's a standard process. We have a CVD reactor. It's the same type of reactor that you would grow silicon in or silicon carbide. It happens to operate at slightly elevated temperatures. We do the process at about 1600 degrees. But the wonderful thing about our reactor is the hot zone has an extremely uniform temperature profile. And since it's a sublimation process, it's all thermally driven. So that becomes very good if you want to make uniform layers of graphene. And so that's one of the reasons for our level of success. The lower left picture is a picture of the reactor, and the schematic shows the various processing gases we can put into the hot zone. Notice we use hydrogen. Hydrogen at 1600 degrees will etch just about every material known to man. And silicon carbide being a very hard material, it has polishing damage. So you need to etch it to remove the polishing damage. So we naturally etch our wafers before we put the graphene on them. And that also gives us an improvement of its properties. So here's the process. We take our as-received wafer, and I chose this one because it shows all those polishing scratches. And then we etch it in 1600 degrees of hydrogen. We remove, something on the order of 200 or 300 nanometers of silicon carbide, and it leaves a flat surface. Well, it's about as flat as you can expect. There's no such thing as buying silicon carbide that's perfectly oriented. So there's always going to be a slight tilt. And after you finish etching it, you will get steps and terraces. And this is an example of the steps and terraces as you would see from an AFM image. And the steps are on the order of 0.25 to 0.5 nanometers high. So it's actually pretty flat. Now, we do our work with graphene. We have a processing conditioning range. We looked at a range of conditions shown here. We found what the optimal conditions were for various pressures of argon flow. We found that using argon gives us more uniform layers than using a lower vacuum. And you can understand why all of this happens by just looking at the phase diagram in this sublimation chart for a given temperature of about 1600 degrees. Notice that we have to be able to sweep away the silicon using a pump system on the order of 10 to the minus 5 torr, and then the carbon is left behind and forms the graphene. So it's actually quite straightforward, and anyone could do this in their basement. And so this is what you get. On the left is when you form graphene on that silicon polar face, and on the right is what you get when you form graphene on the carbon polar face. Notice the morphologies are very different, and it's much easier to see in the high-resolution screen monitors. On the left, on the silicon face, those 0.25 to 0.5 nanometer steps are now much higher. They're like 3, 5, even up to 10 nanometers. So step bunching occurred during the process. But the graphene is extremely thin. It's on the order of 1 or 2 monolayers. Now I'll tell you more about that in a moment. On the right-hand side, morphology is extremely complex. If you look carefully, you can almost make out an image of a step that remains after the growth. Let's try green. You can see one there. Yeah, it looks like a vestige of one here. So it etches erratically, the steps are moving erratically, and you get actually a very thick film of graphene on top, and then you have all these ridges which look like those yellow lines. And so it's a very rough textured surface. So comparing the two is extremely different. So on the left, the graphene grows over the steps, and this is a TEM, and shows the graphene just going over the steps like a carpet. And on the right, you have all this network of ridges, and it reminds us of the back of a giraffe, and so we first called them the giraffe stripes. And yes, indeed, the interns did call them giraffe stripes. And it also turns out they have very different transport properties. Well, first, before we get to the transport properties, let's tell you a little bit about what lies underneath that graphene layer between the graphene and the silicon carbide substrate. For the silicon polar face growth, there turns out to be an interface layer. And the experimental evidence is found by doing this progressive spectra performed by Glenn Jernigan. When he first started off at low temperatures, so this would be this blackish and reddish curve, you get this little lump in this region here. As he increased the temperature, the lump increased. But as it goes to higher and higher temperatures, then another lump appears. And this thing only shows as a shoulder. So what happens is an interface layer forms first, and then the graphene film grows on top of it. This was depicted in a computational way by Ki-Wook Kim and co-workers. This is a picture of this interface layer showing that it's still bonded, albeit not every carbon atom is bonded back to the crystal. It's something on the order of 1 out of 3. As we continue growing, we form the graphene film on top, and that's depicted in this image here, where you see the graphene layer, the interface layer, and the bulk silicon carbide crystal underneath. And this blow-up shows this back bonding of about every 3rd carbon atom. So the structure on the silicon face has this interface layer, and the interface layer consists mainly of carbon atoms, which is still partially bonded to the silicon carbide substrate. On the carbon face, there's no interface layer at all. Okay, transport properties. So naturally, since we're in the semiconductor business, we want to do Hall measurements. So we form little Hall crosses, and as I mentioned before, it's just standard lithography. And you can see an image of one of the crosses. Here's an SEM image in the upper right. And the middle portion shows one of our best samples grown on the carbon face. It's relatively thin, but it's still pretty thick, 6 nanometers, and that means it's about 18 layers of graphene. And it has a mobility of on the order of 27,000. That's at room temperature. So it's pretty good. When you compare it to silicon, it's like 20 times higher. The bottom image shows what happens when you grow on the silicon face. It's very thin. In fact, I can't use an AFM to really see the thickness. It's just noise in the AFM. And so we use this white light interferometry, and you can't see it very well here. But if you look carefully in the monitor, you can see the little edges here, and you can see the graphene going over all the steps. And it's because it's only 1 to 2 monolayers thick. It's 0.3 to 0.6 nanometers thick. And that has a Hall measurement which displays a mobility on the order of 2,000. And lately, we pushed this up closer to 3,000. But it's less than it was for the carbon face case. And the indictment is the interface layer. The interface layer is present for the silicon face material. It's not present for the carbon face material. So somehow it's affecting the transport properties. And to be honest, this is a mystery that still has not been solved. Yes, sir?
The sign of the carriers determined by Hall measurements different in those two cases?
Yes, it is. And I'll tell you right now, there is a reason for all that. It's because graphene is all surface. It's like the thinnest piece of paper you can imagine. And so anything that adsorbs to the surface of graphene is a potential dopant. And it turns out that OH, water vapor, is a dopant, and it makes graphene p-type. This was recently shown in a first principles way by J.S. Sakara and Nardelli. Paper just came out in JAP, I think. So although you see a sign change, in graphene, there's no penalty having an electron or a hole, unlike, say, a gallium arsenide, where p-type gallium arsenide, you're lucky to get mobilities on the order of 100, whereas an n-type in gallium arsenide, you can have 50,000. There's no penalty at all, because there's no mass. So they should all have the same properties. So it's just really the sign. So yeah, a lot of these things I'm sweeping under the rug. It's because there's photoresist on the samples. It's because they've been sitting in the ambient. And no matter how well you think you're cleaning them, unless you subject them to a vacuum anneal, you can't really get reproducible surfaces. So in this graphic on the right, you can see a summary of a large number of these Hall crosses that we measured for the samples. And the red and the black boxes represent the carbon face material, and the blue and the green boxes represent the silicon face material. And notice the silicon face material is always below the carbon face. And that's really the message to take home. There's something limiting the transport properties between the two. The other message to take home is if we look at the sum total of the carbon face data, if we extrapolate it to the intrinsic charge density that you would expect for graphene at room temperature, you would expect a mobility on the order of 200,000. And that is exactly the value that you get for suspended graphene. So this is the same graphene. It's behaving exactly the same. It's just that it's sitting on another surface. Some discussions on how the mobility is limited by scattering can be found in a recent paper by Curtin and APL listed here. Okay.
Excuse me.
Yes.
Do you understand how to control the sheet density on the two faces? You know, you have these plots. Here's another one. Yeah, and you have them there. What's different about the different data? They're all at room temperature.
It's because they've been treated with photoresists. They've been sitting out in the open.
Yeah, different.
Yeah. If you're very careful, and we've been trying to exercise this level of concern, you can get the same result all the time within 10%. For using the standard process of just growing it at 1,560 degrees. It's about 1 times 10 to the 13th, and it's N-type on the silicon face. We haven't done much on the carbon face since this data went out until we learned how to control it to 1 or 2 layers.
Yeah.
Now, we use Raman spectroscopy as another probe, and in this particular case, we can use it as a probe to determine the number of layers of graphene. And so, a single layer of graphene, you would get a spectra which is symmetric, consisting of one Gaussian, whereas if you have a bilayer graphene, you would get a composition of 4 Gaussians summed together in the Raman spectrum. And so using this approach, we mapped out a square. This is about 50 by 50 microns. And we mapped out the number of layers. And you notice that you get these areas that consist mainly of 1 layer separated by areas that are about 1 to 2 layers. And so this is actually the step and terrace pattern that I showed you in the AFM. And you could overlay them, and you will see it overlays precisely. So what's happening is, as you saw in that TEM image earlier, when graphene goes over a step, it tends to have more than 1 layer. And so something is happening in the growth process that forms the graphene that adds a layer. Not well understood. Over here on the right, this is some of the best values we've achieved under an argon-based process. But it's still the same message that I showed you earlier, that the silicon-phase materials always has less mobility than the carbon phase. Okay, so briefly a little bit about the FETs. We've been working with HRL under the DARPA program, and they've created some very nice FETs. These are all pretty much standard FETs using 2 and 3 micron gate length technology. It's well published. The electron and hole mobilities are similar. They're not exactly the same, but they're pretty good. And the cutoff frequencies up to 14 and now even 20 gigahertz have been found for these large gate lengths. Yuming Lin at IBM has published some results up to 200 gigahertz using our wafers, but those gate lengths are 60 nanometers. The image on the bottom left is a Lee-Heighton map of the resistivity in the wafer. So it's a non-contact way of mapping the resistivity across the wafer. And you can see the variation over the wafer is on the order of plus or minus 3%, which is pretty good. It's almost MBE standard for like gallium arsenide or gallium nitride. So it means it's a manufacturable technology. And then here's the IV curves, and you can see some saturation behavior. But there's also some, it turns up a little bit. You can see it turning up here, turning up here. So it's not a well-controlled saturation, and that's because a portion of the short channel is N-type and the other portion is P-type, and so it's actually, you can't really saturate it because you're getting another conduction mechanism. That's an area of research that people are trying to overcome.
How many layers of graphene for those types of devices?
1. Okay, so graphene has a lot of very interesting properties, and we can grow it on silicon carbide, and it means we have a wafer that we can process using standard techniques. We've been doing a lot of work on the silicon face because it has a more uniform morphology, it's not very rough, it's only 1 or at most 2 layers, and so we can do a lot with it, although it's limited in terms of its transport properties compared to the carbon face. So it would be wonderful if we could figure out how to grow it on the carbon face, but make it only 1 or 2 layers thick. And so this next portion of the talk is our work in trying to understand how graphene initiates its nucleation on that carbon polar face. Because remember from the pictures, it looks very different from the silicon face. You don't have that nice regular step and terrace morphology. So the approach that's being done here we go. We make use of a very interesting growth mechanism that Joe Tedesco figured out, that when you change the pressure in the ambient during the graphene growth, you can have parameters where there's no growth of graphene, and you can have parameters where there's continuous films, and in between you can dial in conditions where you just have localized formation of graphene. And so that means I can now, if you will, freeze the growth and take a snapshot of what's going on when the graphene process just starts. And the way we're going to do this is we're going to use electron channeling contrast imaging. So if you have an SEM with some really good forescattering detectors, you could do this here too. And ECCI is of great value because it allows you to see almost three-dimensionally on the flat SEM surface. And so in this particular instance, you can see this little divot here, and I'm going to demonstrate to you that that's a threading screw dislocation. And so you can see dislocations in SEM images. And the way we're going to do that is we're going to take our sample and we're going to carefully march it through Bragg angles, and you will see the change in the electron channeling contrast imaging. Here we go. All right. So ECCI is good because you take your sample, you take your 4 scatter detectors. Suppose you had a particle on the sample. We have the electron beam, and it comes through, and it looks like it creates a shadow. So that gives you that three-dimensional feel in the SEM image. Likewise, if I had, say, a step on a sample, and again the electron beam comes through, the image shows a shadowing. And so you get a three-dimensional feel for the step. And that's the power of it. Normally, if you don't just use SEM in its regular mode, you just get a flat planar image. So if we have a point-like defect, what happens is you see a contrast of light and dark, and the contrast is the key to identifying the source of the dislocation. So let me just walk through the rest of this. So here we go. We now create the graphene under those conditions where we get the localized growth. So we just dial in the pressure and the temperature, and we get the localized growth, and that's what it looks like in a normal SEM. The little black areas are graphene. And notice some of them are larger, some of them are smaller, and they're scattered about in a somewhat chaotic fashion. We can zoom in on some of these features, and now we use ECCI, and you can see that where the graphene is, it's below the surface. And really, that makes complete sense, remember? Because graphene, it's a silicon sublimation process, so when I form graphene, it should be below the surface.
I cannot visualize a dislocation in one monolayer.
Well, it's really threading up from the substrate, and it's just penetrating the surface.
Yeah. So it's coming from the substrate.
Yeah, yeah.
But if you have graphene by itself,
oh,
it should be no dislocation.
Right. What you're going to find out is that the threading screw dislocation is a conduit for silicon sublimation, and that allows the carbon atoms to diffuse out. There we go. And so instead of calling these little areas islands, we call them graphene-covered basins because they're below the surface. And remember, it's the graphene arithmetic, is I have to take 3 layers of silicon carbide to make 1 monolayer of graphene. So it's always going to be below the surface by some fraction of a nanometer. Now, first let's take a look at some of these graphene-covered basins. Here's some of the small ones, and they have this nice hexagonal symmetry, which is very beautiful. And in some cases, you see some with ridges. And then we look to the larger ones, and they start getting more irregular in shape. As you can see in the bottom pictures, sometimes they start colliding with other graphene-covered basins that are being formed, and the walls between them eventually erode away because of the sublimation process. And then you get to even larger graphene-covered basins. And these take on extremely irregular shapes. So all of these things are happening simultaneously. And as you can see in this particular picture, where you have the small, the intermediate, and the large, all happening at the same time. So it's a stochastic process. This nucleation process is stochastic. A nucleation site over here doesn't know what a nucleation site over here is doing. So it's all independent. Okay, so now let's take a closer look. There we go. So when we looked at one of these graphene-covered basins, and you can see it more clearly in the monitors, you can see the spiral pattern. And so right away you're thinking, okay, it's probably a threading screw dislocation is playing a role here. So to determine precisely, we need to look at the contrast of the screw dislocation. And you can see here it goes from light to dark, going from left to right. And we've looked at a lot of these graphene-covered basins, and they all have the same feature. So let's zoom in on this feature. So here's a particular graphene covered basin, and we've changed the Bragg tilt angle of the sample, and we've gone from positive to negative values, and you can't see it on this bottom image, but you can see in the top image that the contrast of that center dot is changing. Near the Bragg angle, you hardly see it at all. And as we go away from the Bragg angle, it looks light to dark, and on this side, it's dark to light. Now, Mark Twigg ran the simulation for the SEM under these electron scattering conditions and demonstrated that screw dislocations should show a light to dark pattern and then a dark to light as you pass through the Bragg angle. But only screw dislocations have this behavior. A threading edge dislocation does not show a change in contrast. So this is the smoking gun, that these little pinpoints that are found at all of these graphene covered basins are threading screw dislocations. And you can remove the graphene, and after removing the graphene, you still see the little pinpoint in the centers. And I have to tell you, we used an extremely highly advanced technological tool to remove the graphene. It was a Q-tip. Now, let's look at some of these graphene-covered basins, but now we're going to use Raman. And we can use Raman in another way. We can use the attenuation of the Raman beam to measure the thickness. And so that's a very convenient process. And so here's two graphene-covered basins, and this is the Raman, and this is the AFM. And they are approximately the same size, so you can overlay them in your mind's eye. The thickness, the red areas, is the thicker areas, and the edge, which is blue and green, this is the thinner areas. And it's sort of hard to read here, but basically it goes from about 1 nanometer to about 14 nanometers. So it's pretty thick in the center. Now look at the AFM images. Dark means it's low, and white means it's high. That's the way the AFM scale is set up. So for these particular graphene basins, this region here and this region here are low. They're below the surface. And the white ridges are high. They're above. So where the graphene is thickest is the area that is also the lowest, and that's because that's where the screw dislocation is located, and it's eroding as the silicon atoms come out, and then the carbon atoms can diffuse out, so naturally the graphene will be thicker there, and you have to go out to the edges because it takes a while for the carbon atoms to diffuse out there. So this all holds together. This particular basin does have a little screw dislocation in it. Okay, so now the next question is, all right, Kurt, you told me that the screw dislocations, but is the numbers, is it a correct density? And so high quality silicon carbide substrates do indeed, people have measured threading screw dislocation densities on the order of 5 times 10 to the third per square centimeter. And that's the typical state-of-the-art stuff that you could buy. And for these samples that I just showed you here, we just took a snapshot, counted up, and we got a number about 5 times 10 to the third. So roughly speaking, every screw dislocation in the bulk silicon carbide crystal is a nucleation site for the growth of graphene. And the graphene is going to be thick at the nucleation site because it appears that the nucleation, the dislocation is a conduit for silicon sublimation, releasing a lot of carbon atoms, and that makes the graphene thicker. And then it spreads out, eventually covering the entire sample. And so that sort of explains why the first image that I showed you, the carbon face growth looks so messy. It was so chaotic. And in the silicon face, screw dislocations don't play a role at all in the growth, at least under the conditions that we've been looking at. So it's dominated by a terrace and step morphology.
If you don't have screw dislocation, you have no growth?
It's sort of hard to grow a silicon carbide boule without a screw dislocation. Actually, there's a patent out there. There's a fellow who patented the idea of just having, creating a crystal where the screw dislocations would be in a very confined region, say less than a square centimeter, and then he would use sublimation to grow out around the edge, and then you would have a wafer where the bad part is only in the center, and all the edges would be perfect. But of course, someone's got to fund that. No. Who's got $1 million? Yes, sir.
This may be an early question, but how does this all compare to graphene on copper?
Actually, it's not an unfair question. It's a completely reasonable question. It's the same material. It has exactly the same properties. Okay? So I can now be a proponent of one over another and allow me to be biased. If you put graphene on copper using the traditional approach, you have to take the graphene off of copper and put it on another substrate to use it. Well, first of all, to do that process, you have to use photoresist. And photoresist you cannot completely remove from graphene. So you've already introduced a problem. Second of all, when you transfer the graphene from the copper to some other material, I don't care how perfect you are, you're going to tear it. You're going to fold it over, and you're going to cause additional imperfections. So, yeah, you could do it. But will it be a high-quality material for devices? It's challenging. And I know there's a guy named Tomas Palacio at MIT who's really worked hard on it. He's done the best job of anyone I've ever known. And his FET results are exactly the same as these FET results. And that was using square centimeter size and a lot of work. Okay, well, let's just move on from this unit. Basically, you need to come up with a way of overcoming the screw dislocation nucleation mechanism to be able to grow on the carbon face. Now, if you had a sample with no screw dislocations, then you could, in principle, be able to grow very high-quality graphene. But it's hard to get a bulk material of silicon carbide without a screw dislocation. But there is one way, and we've tested it out. And so what we did is we formed step-free mesas. Now, I must apologize, I haven't done it on the carbon face yet. I've done it on the silicon face, only because there was another programmatic reason for working with the material. But we have demonstrated that you grow graphene without screw dislocations, and you get very good quality material. Let me get to that. So just to remind you, we have the terracin step morphology. That's the same picture I showed you earlier. Michael Yakes and co-workers used STM microprobes, and they determined that there was a conductance anisotropy associated with the steps. So the steps added resistance. And this is actually well known. Yuming Lin recently published on some of the IBM FETs that the best FETs were always on a terrace. FETs that straddled the step had poor properties. And so it is now well established that you would like to make your high quality FETs on a terrace or a large flat area of graphene. One way of doing this is to take silicon carbide, and I can form mesas on it ahead of time. These don't have to be tall mesas, 1 to 2 microns. And what I will do is I will use silicon carbide epitaxy, and I will grow the steps out until I reach the edge of the mesa. Now what will happen is, at the edge of the mesa, atoms have nowhere to hang on. And so there will be no further epitaxial growth, no further nucleation. And so growth will stop. And what will happen is, after all the steps are grown out, what you're left with is a mesa that's flat. And there's no more steps, there's no more imperfections on it. This only happens if there's no screw dislocation. So if the mesa has a screw dislocation, it's an infinite source of steps. I can never grow it out.
So you can't just get a 2D nucleation process on the top layer of that mesa?
I can. What we did, we grew these mesas specifically to grow 3C silicon carbide on top. And that's a cubic material, and I could nucleate it anywhere on that mesa, and I could grow pretty good single crystal 3C on the mesa. But there's no steps there to grow a hexagonal form of silicon carbide. And what I've done is I've changed the growth conditions in a very careful way so the growth will automatically shut off once all the steps are gone. Now I have a flat mesa, and I subject it to the same graphene growth conditions that I did before, and that's depicted in the ball and stick model in the lower portion of the figure. And this is what a graphene covered mesa looks like. Here's an SEM image on the top, and you don't see any imperfections at all. And we also use ECCI, and we saw nothing. It's flat. It looks like Iowa. On the bottom, this is a mesa that has a screw dislocation. And even in a Namarsky microscope, you can easily see the imperfection. So there will be a small number of mesas that will be perfectly flat because they don't have a screw dislocation. And so I'm going to look for those, and those are the ones I'm going to do my work on. And here's an example of one of these flat mesas, and looking at an AFM picture on the left, and it's basically instrument limited. We found a couple mesas that had little tiny bumps on them. That's shown here on the right. You can see the change in contrast here. And so this area is slightly higher than that area, and for this particular example, the height difference is about 0.6 nanometers. It's just an imperfection. We don't know what causes it, and it only happens on a small number of the mesas. You get away from the imperfection, you look in this area, and it's relatively flat. And this is an ambient AFM, so it's instrument limited, and the roughness is 70 picometers. If I had a UHV AFM, I could probably drop it down an order of magnitude. So, it's very flat. Now remember, when we grew it on the conventional substrates, you get the step and terrace morphology, and the steps were, 5 to 15 nanometers tall. So order of magnitude plus difference. Now let's use Raman spectroscopy. Let's take a look and see what kind of graphene we have there. Once again, we look at the particular 2D peak, and remember, if we have 2 layers of graphene, we have a sum of 4 Lorentzians, and then we can analyze the data based upon this. And here's an example of Raman taken near the edge of one of the mesas, one of the step-free flat mesas. Now, as we get right up to the edge, right here, the full width at half maximum has a large value, and the Raman line shape is complex, consisting of 2 peaks. And that means it's 3 or more layers. When we get more into the center of the region, it consists of 4 peaks, and that's 2 layers. And then I could use the position of the peak. This is the full width at half maximum. Here's the position, and I can measure the strain. And the strain, relatively unstrained. A little bit of strain. Yes, John?
When you do these fits on the Raman spectra, just looking by eye, it doesn't look like all the peaks have the same full width at half maximum. Is that a constraint that's put in, or are they just fit with numbers of peaks?
No, the fits were actually completely unconstrained.
Yeah, well, I mean, I think it would be interesting to try to see, because it looks like when you fit with 4 peaks that the peaks are narrower than the ones when you fit with 2 peaks. So,
well, that is true. I mean, this is just an artifact of the program attempting to duplicate, the spectra. Now, if you go to the original reference by Andreas Ferrari, he was the first guy who did this. There's a theory for where the peaks should be located. Okay. And here, this is our experiment compared to the theory of the position of the peaks. And you can see that they overlap relatively well.
Yeah.
Some deviation for the last one. We're talking about on the order of 9 wave numbers. Yeah. And considering the accuracy of the measurements about 2 wave numbers, that's pretty good. Yeah. And if you look at Andreas's paper, actually our fit's better than his. Yeah. So it's actually a very good fit. And here, let's go to the center of the sample. And in the center, it's all the same color in the full width at half maximum, so it's all about the same thickness. And the peak position is all in about the same position, so it's all about the same strain. And it's slightly strained, but very close to unstrained. And again, comparing it to the conventional substrate, which has this terrace and step morphology, and you can see it's extremely different. These are both on the same scale. So this is what you would see with the step-free and what you see with the conventional. So this is very different in terms of its properties. So we took this one step further. We did some preliminary measurements on the transport properties, and from 4K to 300 Kelvin. And we got mobilities that were roughly 1100 to 1700 and sheet densities on the order of 5 to 3 times 10 to the 12. We compared this. There's actually a paucity of data for bilayer graphene transport properties. But you could find in the Disarma review a compendium of that data. And it's within like 20%. So considering that the flake data that was contained in the review was based upon samples that were on the order of 5 or 10 microns, and this is a 200 micron mesa, the agreement is remarkable. And so this is our current area of research, is to form these mesas, not only in the silicon face but also the carbon face, do the graphene, and start measuring the properties of the monolayer and the bilayer graphene. Because now we get away from the effects of strain, we get away from the effects of steps and morphological difficulties which have been plaguing us in the past. Lastly, we did some experiments, and if we have short growth times, the mesas did not get completely covered with graphene. And this is an example of a mesa which actually has one screw dislocation in it. And you can see the steps spiraling out of the screw dislocation, and the graphene's black, and the graphene is growing on the steps. Now look on the edge, and that's on the lower right image, and you see the black shows like these little fingers. And Taisuke Ota recently demonstrated that carbon diffusion process from a step edge that is not perfectly straight should lead to the finger formation of graphene. And so this picture not only confirms the model of Taisuke, but also indicates that the growth mechanism on these mesas is by carbon diffusion, and it's carbon diffusion from a step edge. And if the screw dislocation was not present here, that means the carbon's all coming from the edge of the sample and growing in. And so now, remember the original Raman that I showed you, where near the edge you had 3 or more layers? It all makes sense because you're starting from that edge and going in, so you expect the edge of the mesa to be thicker than the center. Yeah?
Have you explored its dual use as artwork? Have you explored its dual use as artwork?
It has been suggested, yes, yes. Maybe we need some more pictures. I don't know. Okay. So the summary on the step-free mesas, we've made some great progress, some large area mesas. It's actually now been published in Nanoletters last month. The previous unit on the nucleation was published in Nanoletters last year. We've been able to eliminate the step bunching. We now have a way of forming bilayer graphene, and it allows us to probe the properties of the bilayer graphene as well as to have a laboratory for studying the growth mechanism and carbon diffusion. So that becomes very interesting. So, yep, we've made a lot of progress learning a little bit of how graphene forms on silicon carbide. There's a lot more to do, of course, and it's an exciting area, and we're having a lot of fun with it. And as I mentioned before, there's a lot of people who contributed to the work that I showed here, and I hope I got everyone's name on here. They've been, it's been a wonderful group working with, and I really thank all of them. And I thank you for letting me show you the results here today.
Quick question. So another way to open up the band gap is to pattern the graphene into nanoribbons.
The ribbons, yeah.
Have you tried scaling down the mesas to really small dimensions to see if you can
It would have to be really small dimensions. You're looking at 20 nanometers or less. We've given some wafers to Deputy Jenna and Grace Shing at Notre Dame. They've actually just published a paper on some 10 nanometer ribbons. Walter here, what he does is he patterns the sample to make these the small edges, these ribbons, and then he does very short growths, so that even though these little ribbons he makes are on the order of half a micron, the amount of graphene in it is even smaller. And he's claiming that he's getting a band gap there, although there's certainly a lot of controversy in that. We haven't tried it. I think it might be interesting, especially to pattern the graphene, to study more about what happens on these other surfaces. We had a brief discussion about that earlier this morning.
Any other questions?
In terms of polycrystalline grain size, how does that enter into this type of growth? Are these mostly single grains, or are they within this 2D layer, or are you getting multiple grain boundaries?
For the conventional silicon-based material, as far as we know, it's all single crystal. We have done some limited STM work, and others have done that too, like Joe Strosio. And occasionally you can find defects, but not often. I'm not saying that that's an absolute. I think a lot more work needs to be done. And when you start looking at STM images, you need to look at hundreds of them to find a problem. Now, for the carbon face, that's a completely different story. That material is probably all polycrystalline. And I would call it rotationally faulted polycrystalline, and there's tremendous evidence already in the literature for that interpretation. We now have a good reason for understanding why it arises that way. It's because it's nucleating at all these locations. There will be preferential angles, but one location versus another, there's no communication, so you get a range of angles. When we go to the step-free mesas, not clear. We have some samples, and it looks like you get 3 regions that are all oriented one way, but there's a grain boundary between them. And I think that's potentially an exciting area to look into, because then you could look at the effects of a grain boundary on transport properties, for example. So yeah, that's an open question.
So in terms of the limitations of transport, you're thinking it's really the interfacial layers that are most highly impacting your transport.
It's too much of a smoking gun to ignore.
Okay.
I mean, I look at the silicon versus the carbon-based material, and they're almost an order of magnitude different in mobility. And there's no other reason for it. I mean, even the carbon-based material is not even single crystal. It beats the pants off of the other one. So there has to be another reason for it.
Back there?
Yeah. So for the silicon phase, graphene, you have a transition layer, right?
Yes.
When you lift off the graphene, will the transition layer come up together or no?
Oh, that's a very interesting question. We have made attempts trying to peel off graphene on the silicon face material. They have not been successful. We have been able to peel it off the carbon face. That has been successful. And in fact, while I was being introduced, there was an email that just came through from one of my collaborators at NRL. We had transferred some of the carbon face material to a transparent substrate, and he just used it and demonstrated it as a saturable absorber, i.e., he made a pulsed laser out of it in the infrared, and it's the first time it's ever been done. So it does work.
Then if you are not able to peel out, and then if you fabricate device on it using the graphene, would the transition layer line affect the performance of the device?
Well, if I could peel it off and the interface layer was still there, I don't know. It's too speculative. I have no idea. I do know there's another person in our circle who she's developing chemical scissioning methods for peeling off graphene. She gave her first presentation at last year's ABS meeting, and I know she's working very hard on it right now. We have our fingers crossed to see if she'll make some progress.
So is this intercalation of hydrogen?
No, No,
Do you
we're
think
doing that
there's any hope
separately.
To do transport measurements on hydrogen intercalated silicon phase, where it's decoupled from the interface?
Yes, yes. Ginger Wheeler is in the process of putting the finishing touches on that.
What's the mobility?
Her latest result was a mobility of 3,400. And when you lift, when you convert the interface layer, it becomes 2 layers of graphene.
It's bilayer.
It's bilayer, and it goes P-type because it's no longer being subjected by the transfer, charge transfer from the unsaturated silicon orbitals.
So you should intercalate under the buffer layer.
Yeah, it probably goes through it all. I mean, you can't.
Yeah, but
Control
if
one
you
or
just
the other.
started without graphene, only buffer layer, then you would have a single layer of graphene.
Yes, and that was the approach taken by OTA with Eli Rotenberg when they did that ARPAS data for the plasmarons. And it's a nice thing. It was a beautiful piece of work.
Any other questions? If not, let's thank our speaker again.